Okay, this is the first lecture for Chapter 7, and this is for Trends of the Periodic Table. So we went over this story before in regards to how the table was kind of put together, or the development and the naming of some of these properties. And the one name we mentioned that kind of stands over the others was Dmitry Mendeleev, and he was the guy that kind of made the discovery or the prediction that we had some elements that were not known at the time, but he predicted their properties. And other people that did kind of the same thing is this Meyer gentleman, and he did almost the exact same thing and did everything that Mendeleev did, but he doesn't really get credit for it because Mendeleev, probably his personality was pretty large. But this is kind of a neat little table here if you wanted to pause it and take a look at it. It's kind of neat to see that, you know, how old some of these elements are. Some of these are very, very old as far as their discoveries go. Anyways. So some other things just to take a look at. This is one of the predictions that Mendeleev made with this ecosilicon element, and just how what he predicted it would be and actually how it did turn out. Amazing that he was able to do this without actually having the elements, but it just goes to show that the periodic table has these characteristics that are predictable. There's trends in how these things tend to work out. So he used that to discover some of these new elements. So some of the things that we're going to be looking at in this chapter, and you'll become pretty good at this, is the sizes, both of just the atomic radius and the ions, the energies involved in losing or gaining electrons, actually just losing, and then in gaining electrons, the affinities. We'll look at all those. And then some of the trends in regards to some of the different families. We'll talk about some of those too. So first thing on our list is the effective nuclear charge, which goes into why some electrons, or excuse me, why some atoms gain electrons or lose them. So the example we're using here in the book is sodium. And as you know, sodium has, I guess, 11 protons and 11 electrons. And then you look at how these electrons are arranged, and we talked about how they have these shells. There's 2 in the inner core, and then there's 8. Let's see, I'll draw a little picture here. So we got a little sodium, and there's 2 on the inner 1s, and then there's 8 on the next level, and then on that third level, there's just 1 electron out there. So on the next slide here, we'll discuss how we kind of come to the numbers that we get for how well it loses electrons. So this is a little formula here, and it's called the effective nuclear charge of the exterior electron. And it's composed of 2 things. One is the atomic number, and this one is the shielding factor. So as an example, if I remember correctly, we can simply say, okay, this is 11, the atomic number is 11. And if we look at the shielding factor, we can simply look at not the electron itself, which is on the exterior, but all the other electrons below that shell. So that 1 electron we saw on the previous slide was on the outside, and then there's 10 interior electrons that are shielding that 1 electron, which gives us an effective nuclear charge value of simply 1. And there's this other idea which is called Slater's rules. Let me draw that out here. Slater's rules. And what that goes into, I know this is scribble, is electrons which are on the same level are given a value of 0.35, and electrons that are on the level below are giving a value of 0.85. And this is in regards to shielding. So if we go through and say with sodium, for example, well, there are no electrons on the same level. It's just the 1. But on the interior level, there is 8 of them, 8 interior electrons, and I didn't do the math here, so 64 plus 4, so I don't know. You should get a value which is fairly similar to 1 in regards to its shielding. And actually, no, that's not anywhere near as close. I guess it would have to be close to 10 to have that same effect. But I don't have the calculator handy, so it should be something fairly close. Moving along. All right, atomic radius is simply, or the ion bond length is simply the distance of each of these guys independently, and you would just have to add them up. So for example, if this was HCl and I wanted to know what the bonding radius this was, I would simply have to determine what the bonding radius is for hydrogen and the bonding radius for chlorine, and then add those distances up. So we'll do a couple examples like that in class. Alright, this is the important stuff that we'll be getting to. We'll talk a lot about this. If we can just look at this one chart, it really answers all the other questions that we'll come into in regards to ionization energy and electron affinity. Even metallic character can come in there as well. So, looking at this, if we're moving, I'm going to go left to right. So if we're moving in the opposite direction that we have on this chart here, what we're going to notice is in any given row, pick a row, it doesn't matter, any given row, you're adding protons to the center of the atom. So if I think of that in regards to being like a magnet, my positive magnet is getting larger on the right side as compared to what it was on the left side. So it's going to pull electrons more in. So as I'm adding electrons on the outside, that magnet on the inside is becoming stronger and is pulling the shells, the electrons, more in. So the size of the atom becomes smaller. That's a little bit tricky. Looking at the top to bottom, not so tricky. Why is helium so much smaller than xenon? Well, you're adding shells each time. So here I start off, there's that same shell, but now I have a new one on the outside. And then you can just keep this trend going as you move down. So they get larger. So easy enough. Okay, ions. We have a slight different idea going on here. Is looking at the first three in red here, we'll notice that lithium, of course, loses one electron. Loses one electron. Beryllium loses 2 electrons, and boron loses 3. So again, we're adding protons every time to the interior. So in comparison, this is getting larger and larger, yet I'm losing electrons each time. So it's an equivalent amount of electrons. So just because I'm having a stronger positive interior, the atom gets smaller and smaller each time. And this trend continues going down these columns as well, from left to right. So I have the same trend going here as I did up here. The only difference is these, of course, are larger because, again, you have more shells. But then we have to do a different idea on the, for example, oxygen in comparison to fluorine. Oxygen is going to gain 2 electrons and fluorine is going to gain 1. But again, this has a larger comparative magnet, if we will, than this one here, greater positive than this one does. And it's going to pull it in further still. So they both have similar amount of electrons, but the fluorine has more protons, so therefore it's going to be smaller. That's a lot going on. So what we didn't mention on that previous slide, because it's over here, is a bunch of atoms that are considered isoelectronic, which means they all have the same number of electrons. So to make this conversation work, let's get rid of a few here. And I think with that, we're pretty good. We'll get rid of these guys too. All of these atoms have the same number of electrons, which I believe is 10. So oxygen gains 2 electrons to get to an electron configuration of neon, so 10 electrons. Fluorine gains 1, 10 electrons. Sodium loses 1, 10 electrons. And so on down the line. They all do the same thing. They all have 10 electrons. The difference would be is the number of protons. So they all have an equal number of electrons, but aluminum has the most protons, so therefore that one is going to have the strongest relative magnet, and oxygen is going to have the smallest number of protons comparatively. So that one's going to be the largest of the bunch, and you can just look at the value, the 1.26, in comparison down the line. Okay, so this is a good place to stop. We've gone about 10 plus minutes in, so we'll start lecture number 2 after this one.